Wisconsin Robotics is a student organization at the University Wisconsin-Madison, comprised entirely of student volunteers. So Wisconsin Robotics is currently building a robot for the University Rover Challenge. The robot we're designing, name is Insomnia. The team is organized into 3 core subteams: mechanical, embedded, and software. Each subteam is responsible for the design and implementation of their eponymous systems on Insomnia. Unifying these subteams is the team leadership, comprised of 3 elected positions of president, vice president, and treasurer, as well as the leaders of each subteam. The leadership meets once a week to make administrative decisions, delegate technical tasks, and keep the team on track.
So when we were designing Insomnia, we tried to follow 3 pretty big core tenets, which were modularity, being able to adjust it easily, and function over form. So it doesn't have to be pretty, it just has to work. The current weight of the robot is around 32 kilograms. We still have to add the arm and the onboard science kit. Even after adding those, we should remain under 40 kilograms. The frame was designed to be able to quickly change, so we used square tube and plastic connectors that connect the corners in order to easily be able to modify it. So changing it literally just you pull the connector, you change the lengths or the angles, and you put it back together. We could entirely disassemble and rebuild Insomnia within a day if we had to. Because the rocker bogie needs to move at slow speeds due to the lack of dynamic suspension, we designed Insomnia to move at a slower speed. At peak efficiency, our robot moves at 3.5 feet per second, which isn't that fast if you think about it, but the rocker bogie kind of necessitates that due to the lack of dynamic suspension. While it is relatively slow, we expect to make up for lost time when traversing terrain. The frame and drivetrain were specifically designed to easily handle the terrain traversing task. Insomnia can easily climb 20 inches and 0-point turn to get around anything above that. Insomnia's wheels follow those same core design philosophies. The wheel's driving motor is actually inside of the wheel, which keeps it safe from the environment. A Kevlar shell encases the entire wheel as well. We specifically chose Kevlar over something like carbon fiber because Kevlar actually does provide a better piercing resistance or impact resistance. The wheels are easily swapped out. We could take all 6 of them and replace them within 30 seconds if we had to.
For the arm, there are 5 degrees of freedom: turntable, shoulder, elbow, wrist, and the rotation of the claw. The first degree of freedom is the rotation of the entire arm on the turntable. For the turntable, we are using a 33 foot-pound gear motor that is offset from the axis of rotation with chain and sprockets. For the shoulder, we are using a linear actuator with 330 pounds of force because the 5 kilogram mass on the end of the claw creates a 44 foot-pound torque on the shoulder axis. The elbow has the same 33 foot-pound gear motor that's on the turntable. It's geared up with chain to a 2-to-1 gear ratio to give us a safety factor of 2. We are using the same gear motor also for the wrist. However, since there is a much smaller moment arm from the heavy object, we are only using a 1-to-1 gear ratio through the chain offset. This offset decreases the moment arm of the weight of the motor on the shoulder. For the rotation of the claw on the wrist, we are using a 212 ounce-inch servo with a 7.5-to-1 gear ratio through a belt system to increase the torque output. We are using that same 212 ounce-inch servo for the claw. However, for the gripping of the claw, we have a 5-to-1 gear ratio through a smaller belt. We designed this arm specifically for the equipment servicing task, astronaut assistance task, and science task. The claw stays the same for both the equipment servicing task and the astronaut assistance task, but the tips are interchangeable for each. The tips for the astronaut assistance task are tapered to be able to clamp around the hand tools and the 5 kilogram object. We will store these objects in a box on board the robot to transport them to the astronaut. The tips will change for the equipment servicing task. These tips will create a large surface area to make it easier to grip the fuel can, fuel tank cap, and the oxygen tank regulator. For the science task, the claw is being replaced by the science attachment. For the science attachment, we are obtaining a soil sample that we can deposit in a container on the robot. For collecting the soil sample, we are simply plunging a tube into the ground. If needed, there will be a serrated edge on the tube. We're using a servo-driven rack and pinion system to deposit the sample into the holding container. We will transport this to the base station to do analysis on the sample.
The Aries finals include the astronaut assistance task and the equipment servicing task, both of which depend heavily on the robot's actuator. In order to ensure accurate and consistent control of the arm, we have designed our own motor controllers, which implements a custom control algorithm and interpret the quadrature encoder feedback. This allowed us to implement a proportional differential, or PD, controller, which gives us the strength to carry the objects in the astronaut assistance task, as well as the precision manipulation required for the equipment servicing task.
We chose to use Talon motor controllers for our drive motors. They're the same controllers that FRC teams use and are able to output the power that we need reliably. Our embedded software uses FreeRTOS, a real-time operating system running on an Atmel ABR XMega microcontroller. FreeRTOS allows us to deterministically schedule tasks and satisfy the strict timing requirements of an embedded system. The XMega is similar to the Arduino, and so it's very easy for the team to adopt, and also has the power to handle FreeRTOS. Several sensors are handled by the embedded system. We have an inertial measurement unit that tracks our acceleration and rotation, and we also have encoders that measure the wheel rotation speed. With PID control, we'll be able to have very smooth and clean movement. Additionally, we have a GPS that will help us keep track of our position and locate our objectives. These sensors also provide feedback to the higher level software system so that it can make educated decisions.
So Insomnia's power system has support for 3.3, 5, 12, 19, and 24 volt logic, and it's equipped with 240 watt hours of power from our lithium iron phosphate battery. We'll be integrating a simple analog voltage sensor to track our battery charge levels, as well as an analog current sensor to take advantage of the Hall effect to isolate the secondary sensing circuit from the primary current being sensed. Each motor is short circuit and overcurrent protected with Type 1 automatic reset circuit breakers. Specifications for these were based mostly on stall currents and expected temperatures at competition. The system features emergency stop capabilities for all actuators and drive motors that can be activated on board with a push-button switch or via software through a mechanical relay, all without interrupting any other digital logic.
Next up, we have the communication system. We met this challenge by operating on the 70 centimeter or 420 megahertz radio band, where the lower frequencies help us punch through any obstacles between us and our rover. A Zagel XC420M radio module handles data processing, kind of like a Wi-Fi network interface card. A steerable, highly directional Yagi antenna at the base station lets us focus our transmission power directly at the robot to maximize signal strength. Finally, in case this stuff all fails, we have an XB acting as a backup. All this might be a bit overkill, but it means we'll be confident that our communication system won't fail in the field.
The Badger control system is our unified GUI for connecting to and controlling our robots. It issues commands to Awake, is responsible for selecting the appropriate drive mode, controlling the arm and claw, and collecting and compiling all necessary sensor data and forwarding to the appropriate location. Should we lose primary connection, we will then fall back onto our backup connection through the XBs. The XBs are slower than the primary connection, but have a significantly larger range than our primary connection. As a result, the backup drive system only receives bare-bones sensor data from the onboard laser rangefinder, GPS, IMU, and compass.
Upon losing connection with both primary and backup communications, Insomnia will resort to autonomous navigation. With the help of a GPS and a laser rangefinder, this will be done in one of two ways. If not sufficiently close to a destination, such as the equipment service task, it will backtrack to the last known location with a good signal strength. If Insomnia is close enough, it will then proceed to the destination. This is accomplished by the LRF gathering the sensor data, smoothing it through our algorithms, and then consolidating the data into objects. From there, the robot will decide the best path and send the appropriate drive commands all in real time.
Insomnia's video streaming software was actually built in-house, and we chose to do this because all the existing solutions didn't have the flexibility we were looking for. On the broadcast side, it uses Microsoft Media Foundation to control webcams, and then it samples them at relatively low resolutions. The software on this side is actually able to support multiple cameras, so the user can switch between them, but it will only actually broadcast one back in order to save on the bandwidth. So the playback software is a WPF application that simply receives frames from the broadcaster and displays them. It communicates via UDP and has a bit of redundancy built in so that any dropped packets don't result in excessive latency of what's displayed on the screen.
For the past 2 years, we've been using something called the JAWS protocol to communicate with our robots. JAWS defines the data format and method of communication between different robotic systems. For the past 2 years, we've been building and refining Badger JAWS, our C# implementation of the JAWS protocol. Badger JAWS provides an API that abstracts all network communications and handles the scheduling and execution of services such as the discovery of remote services, liveness, remote driving, and sensor data transmission.
For the science task, we've chosen our instruments carefully with the goal of maximizing our chances of detecting life while avoiding false positives. We decided to start with a temperature and humidity sensor, then we'll use 3 wavelengths of light to analyze the sample we'll take from the desert. Optical spectroscopy lets us examine the molecules that make up our rock sample. If life is present, we expect to find absorption lines representing large organic molecules. Our optical spectrometer is right here. As you can see, light enters from this side. It goes through a diffraction grating and is split up into different wavelengths, and then a webcam connected by a USB port analyzes the data. X-ray wavelengths are about the same size as the distance between atoms in a crystal. Our equipment works by producing X-rays using an X-ray tube and bouncing them off atoms in the crystal lattice. The resulting diffraction patterns contain valuable information about the details of the crystal structure. We hope to be able to identify sedimentary rocks such as limestone that can only form in the presence of water. Gamma rays, the highest energy photons, let us look at processes taking place on the smallest scales inside the nuclei of atoms. Notably, by mounting a gamma ray spectrometer on the robots, we expect to find signs of the hydrogen in water, even if it's buried under as much as a meter of soil.
Wisconsin Robotics has invested a substantial amount of time and effort into building our robot Insomnia. We expect to be able to perform at a high level at URC this coming June.